All right, guys, second time I'm recording this video, so I'm a bit grumpy because my mic cut off for this video and for the big problem that we did today. Anyways, so to complete the lecture for today, we're looking at the general equations of motion for planar motion, right? And the special case that I wanted to talk about something that dynamics people love talking about is rolling without slip. I think this guy might be dead. Can't tell. All right, so for rolling without slip, what do we have? So we have, say we have wheel, which is rolling without slipping. And the interesting thing here is that at the point of contact, let's call that guy O, there is no movement that is happening. So the velocity at that point is equal to 0, and it's known as the instantaneous center of rotation. So if we look at that point G, and if there is, let's say we have an angular velocity term and an angular acceleration term. So this guy is moving forward, so it's going to roll that way, so there's going to be that, and it's going to have an acceleration. Right? So let's call this vector from O to G, let's say that that is R of G relative to O. Right? And the frame of reference that we're looking at is our regular XY frame. So from the kinematics of the problem, if I look at the kinematics, the velocity of the point G, we know that the instantaneous rotation is happening above the point O, right? So if I put my rotating frame of reference there, I have VO, which is going to equal what? 0, plus the velocity of G relative to O, which is going to equal 0 because the G remains fixed with respect to O. So I only have that term. So omega crossed with R of G relative to O. And if I do the math, write it out in vectorial form, the scalar is just minus omega R I hat. So you can see that the velocity of the center G is usually, the scalar term is just equal to omega R. And similarly, I can get AG by differentiating this term. So R of G with respect to O, as this thing is moving, it does not change, right? So the acceleration of the point G is just omega dot crossed with R of G relative to O, and that's just equal to alpha crossed with R of G relative to O. And if you write that out in scalar term, that is just equal to, if you do the math for this specific case, it's minus alpha R I hat, right? And this is the kinematics of the problem. And now looking at the kinetics of the problem, if I do my force equilibrium in the x direction, right? So that's going to be all the forces that act on my body from my free body diagram plus m times AGX, right? And I know that the scalar value here is just alpha r, so it just turns out to be equal to m alpha r like that. In the y direction, all the forces that act in the y direction equal MAGY, which is going to equal 0, right? And for this specific case, I can take moments about the instantaneous center of rotation O, and that is just equal to my mass moment of inertia about the point O times the angular acceleration. So that completes and this expression here is only valid for rolling. Because if there's rolling not happening and there's slipping happening, you can't use this expression, right? So only for rolling without slip. Okay? So this is what we need for our course, but an interesting thing to note is what is the acceleration of the point O? I'm not going to ask you guys a question on this, but it's important to know for when you look at machine design, machine dynamics, and gearing and stuff. So what is now intuitively you're going to just say 0, it's not moving, right? Nope, it's incorrect, because if I take a look at my rigid body motion, the acceleration of the point O, now we are moving our frame of reference to G, so that's going to be the acceleration of that point because it's moving, plus, is there going to be a Coriolis term? No, because these 2 points do not move relative to each other, so there's no Coriolis term. So then you have an alpha term, so alpha crossed with R. Now you're looking at O with respect to G, right? So that's the second term over there. Plus you have your centrifugal term, so that's going to be omega crossed with R of O relative to G, right? And what's AG equal to? We saw that this guy is just equal to alpha crossed with R of G relative to O, right? So alpha plus R of G relative to O, so that's that term, plus alpha crossed with R of O relative to G, plus omega crossed with R of O relative to G, right? Now, interestingly enough, what you see is that R of G relative to O, R of O relative to G, so these two terms just cancel each other out. So the acceleration of the point O is actually equal to the centrifugal acceleration, which comes as a rotation, and that's just equal to omega crossed with R of O relative to G. And this is an interesting term because it appears a lot in gearing and machine dynamics, so just wanted to give you guys this. All right? With that, let's look at a problem.